Daha önceki dersimizde hatırlıyorsanız şeye kadar geldik. Adı neydi? Şu anda hala resistif şeyleri sadece içinde direnç içeren devreleri pasif eleman olarak pasif böyle değil. Eleman olarak sadece direnç içeren devrelerden konuşuyorduk. Tevenin'e kadar gelmiştik. Bir şey mi sormak istiyor? İngilizceye geçeceğim. Sordunuz.
BBC mikrofonu açık unutmuş olabilir hocam.
BBC'nin burada ne işi var? Neyse bir şekilde halledeceğiz. Okay, let's start. Pardon, başlamadan önce şey olarak ekleyeyim. Adı neydi? Hatırlarsanız geçen haftalarda söylemiştim. Önümüzdeki hafta içinde ben yokum ama ders olarak asistanlar size soru çözecekler. Hani cuma günü yapmaları gerekeni perşembe ve cuma beraber yapacaklar. Bu cumada sizle uğraşmayacağım. Zaten ödevinizi verdim. Görüyorsunuz ödevlerle ilgili bazı küçük serzenişler var ama normal bir şey bu. Yeni bir şey öğreneceksiniz. Merak etmeyin, simülasyon öğrenmek kötü bir şey değil. Bu kadar da direnç göstermemeye çalışın. Evet, ödevler herkes için. Sadece lab'ı alanlar için değil, ödev dersi alan herkes için. Haberiniz olsun. Okay, now let's go to the Thevenin equivalent circuits. Before we have let me just go back a little slides. When we have just two, and this is kind of good. When we have two terminals like this, we don't really want to care about what is on this portion of the circuitry. Maybe a simple representation of that side will be sufficient for our analysis. That's what Thevenin and later we'll see as the Norton's equivalent circuits does. Looking from these two terminals A and B, when we look back in here, we want to put a simple, the simplest circuit possible to represent what is all these things above this portion does. One way of doing this is using a voltage source and a resistance in series with that. As I said before, if we had a parallel resistance in here, that wouldn't mean anything. We could easily just ignore that resistance. And the Thevenin equivalent circuitry is a voltage source, a dependent and independent voltage source in series with a parallel, with a series resistance. We call them the Thevenin voltage and the Thevenin resistance of that circuitry. Just looking at this and the way we did source transformation before, you can also say that we have another equivalent circuitry that is composed of a current source. This time it will be in parallel with a resistive element. Anyway, now when we just kind of simplify the circuitry this way, it will be valid for any device that is attached to this AB surfaces, AB terminals. It will be very simplistic for us from this time on. Just let me put it this way: after realizing this equivalent circuitry, it will be very easy for us to determine what's going on between the terminals A and B. But there is a catch. We have to somehow determine this VTH, the Thevenin voltage, and the Thevenin resistance of that circuitry. There are many ways of doing this. In fact, the best, not the easiest way, the straightforward way is trying to use the source transformation over and over up till we end up with something like this. But there are easier ways of doing this. The one way of doing it is just assuming it in this formation and just instead of RL, use the extreme values. The first extreme value will be just the open circuit version of this. Open circuit version, meaning that RL is equal to infinity. The resistance between those two terminals are infinite. Now, if there will no load resistance at these terminals A and B, what will be the voltage we'll be reading from the terminals? The voltage difference between the terminal A and B. Any ideas? We've got 118 people in here. I mean, at least one of you should have an idea. If there will be an open circuit in here, the voltage we read between those two terminals, A, B, will be the Thevenin voltage. Since there won't be any currents passing through this thing when the RL is open circuit, we can directly see that equivalent voltage source. That will be Thevenin voltage. If we had a multimeter and we had the real circuitry in here, directly using the multimeter, we can obtain this value by just measuring the open circuit, just open circuit voltage of the between the terminals A and B. How about the resistance value? I mean, you see, at least from a practical perspective, calculating the V open circuit will give us the Thevenin voltage. But how about the current passing, or how about the resistive value, the RTH? For that, we use the other extreme. That means that we directly short circuit these two terminals. Instead of RL, we say that, okay, the resistance between those two values is simply 0. Now, at this point, the current passing through this can be calculated. And if we divide the voltage through that current, we can directly obtain the resistive value, the RTH. From a practical point, I mean, if you were just looking at the circuitry in the lab, you can just short circuit these two terminals and measure the current passing through that. That will be the current, that will be the short circuit current passing through those terminals. And if you divide the voltage you calculated or you measured from the open terminal voltages, by dividing that to the short circuit current, you'll obtain RTH. So that's it. From a practical point of view, it's very easy to find the Thevenin equivalent of a circuitry. Just open circuit the terminals, measure the voltage, then short circuit the terminals, measure the current there. The open circuit voltage will give you the VTH value, and the ratio of VTH to the short circuit current will give you the RTH value. This also just kind of gives us something else. I mean, and this is the illustration, Thevenin illustration. But using the source transformation, when I obtain something like this, I know that I can turn this thing into a current source in parallel with a resistive value. Now, the nice thing is we call this the Norton equivalent of a circuitry. Rn value or R Norton is exactly equal to the R Thevenin value. So all you have to do is calculate I of n, which we know from our previous lectures that In will be VTH divided by the resistive value. So Rn is since Rn is equal to R Thevenin, that means that In can be found by VTH divided by RTH. This is very useful. On many occasions, you'll see that we'll be using source transformation, or then the Thevenin theorem and the Norton theorem, or Thevenin equivalent circuitry. Then the dual operator of that, the dual circuitry is the Norton equivalent circuitry, to simplify the circuits and just make the analysis easier. Now, let's try to find the Thevenin and Norton equivalent of this circuitry in here. We can do this, by the way, all the knowledge we had up to this class, using all those, we can do this example in 3 different ways. The first one, we can just use the open circuit and the short circuit voltages, the open circuit voltage and short circuit currents, just the way we just learned in 2 or 3 slides before. We just in order to calculate the VTH, we just open circuit the terminals A and B, just remove this load resistance from here, assume that it is open circuit, and do the analysis accordingly. And if you just do it this way, the node voltage on here will be open circuit. I mean, nothing will change. And doing a simple node analysis on this circuit, let me put it as 1, will give us the open circuit voltage. That is V open circuit minus 4 divided by 2. That is the current passing through that. That's our assumption. Will be equal to the current coming to that node. That is 2 milliamps. So the summation, I mean, this node equation enables us to calculate V open circuit easily. Just put this 2 microamps to the other side of the equation, multiply by 2 kilo ohms, you'll obtain the micro and the kilo versions will cancel each other. You'll obtain 4, and when you just move this 4 to the other side of the equation, you'll end up that VTH can be calculated directly as 8 volts. How is it coming up to now? Does anybody have problems up to now? Is it coming all good? Thanks for not answering. Let's try to go to the short circuit analysis. I mean, just short circuit these two terminals, the terminals in here, just short circuit them, and try to calculate the current passing through that. That will give us the Norton current. Anyway, just this time, I mean, assume V1 in here, the same thing, and just do the analysis. I mean, just simple node analysis is still work. This time V1 is the voltage in here, our assumption. So let's assume that 3 currents are going, and this 2 of them are leaving the circuit, the node. 1 of them is coming in. So the summation of these 2 will give 2 milliamps. The voltage on here is, I mean, the current getting out of this node on this direction is, let me write it in red in here. This red one is V1 minus 4 divided by 2. That is this portion. The current getting out of the node on this direction, man, I cannot see yellow in here. I didn't like it. Maybe greenish is better. Okay. This current is V1, no voltage sources in here, divided by 3 kilo ohms directly, this one. And 2 milliamps is the current coming into that node. So this node equation has to be satisfied. Yeah, we'll find a value for V1, but that won't be the real V1. We want to calculate the current, this green current using that V1 value. When you simplify this node equation, you'll find that V1 can be calculated as 4.8. And if you divide that by 3 kilo ohms, you'll find the current, the short circuit current, that is 1.6 milliamps. Now, the resistive value, the equivalent Thevenin resistance of that circuitry is V Thevenin, the open circuit voltage between between the terminals A and B divided by the short circuit current, 8 divided by 1.6 milliamp, don't forget the million here, you'll end up with 5 kilo ohms, meaning that the equivalent Thevenin circuitry will be in this form, 8 volt voltage source in series with a 5 kilo ohm resistance, and the corresponding Norton equivalent circuitry for this circuit is a current source of 1.6 milliamps in parallel with a 5K resistive value. How is it up till here? This is the first method using open circuit voltage and short circuit current technique. Okay. The second method, I mean, I can easily use, let me go back all here, source transformation in here. Just convert this circuitry into a current source in parallel with the resistive value. This will be the current, as you can remember, 4 divided by 2, that's 2 amps. It's 2 milliamps, really. The resistive value will stay the same. Now, that is in parallel with another current source. That means that I can adapt these two current sources. Instead of 2, I can just write 2 plus 2, that will be 4. Now I combine all these three. To go any further, I can just do another current transformation, just a source transformation on this, and just convert that into a voltage source in series with a resistor, the same resistance in here, and that resistance will be just the summation of these two. And the value of the voltage source can be found by just multiplying the current source value with the resistance value. And this is what I end up with. The same thing as I found before. And if I want to turn this Thevenin equivalent into a Norton equivalent circuitry, all I have to do is make this resistance in parallel with a current source, which value can be found by just dividing the 8 volts by the 5 kiloamp value, that is 1.6 milliamps. The same thing can be obtained. Now the third method is kind of fancy, but still can be doable. It's nice. We can use independent source deactivation technique in conjunction with the linear, it's just superposition. The whole thing is a linear system, and linear systems satisfy something called a superposition principle. The resistance value of the circuitry, the equivalent resistance of the circuitry, can be found using this independent source deactivation technique. That is, we will short circuit the voltage sources and open circuit the current sources, and look from the terminals back in and just calculate the equivalent resistance. I mean, just short circuit the voltage source, put an open circuit instead of the current source. All you'll see is two resistances in parallel with each other. That is the total Thevenin or Norton resistance, you can call it, equivalent resistance of that circuitry. See, it's so nice. I mean, that means that these two can be just added up. We'll end up with 5 kilo ohms, which was the value we found before, 5 kilo ohms. That is our Thevenin. But to find the voltage corresponding to Thevenin voltage or the Norton current, we'll use something called superposition. We could have just, instead of using superposition, we could just go and calculate the, let me put it this way, where was that open circuit? This open circuit voltage and find VTH, but we already done that. That's why I'll try to use some other methodology in here, so you can see, you can also learn this one. Superposition means that put only one current or voltage source in the circuitry, and just use an equivalent circuitry for the rest of them. That is, put short circuits for voltage sources, for the remaining voltage sources, and open circuit for the remaining current sources. For each source, repeat the same procedure and calculate using nodal analysis or whichever you want. Calculate the voltage value or the current value you're looking for, and at the end, just sum them up. In here, we first use this voltage source and open circuit the current source value, and calculate the VOH in here, which can easily be calculated in here. As you can see, the voltage between those two terminals, since no current is passing through here, is directly 4 volts. Now the second way is, this time we short the voltage source and use the current source as the only source in the circuitry, and calculate the voltage on this side. Now, when you short circuit in here, you can see that the current will pass only from this side, and the voltage we'll see here will be the voltage in here, exactly between those two terminals, and that will be 2 kilo ohms multiplied by 2 milliamps, 4. The total voltage of the applied on the total voltage, you can see from the terminals A and B, will be summation of these two, which is 4 and plus 4 is 8. That's it. That's the way you get the Thevenin voltage. See, we got exactly the same values as we had on the previous two methods. 8 volts for the Thevenin voltage, 5 kilo ohms for the Thevenin resistance. All three methods can be used for the analysis of circuits and finding the corresponding Thevenin and Norton equivalent circuitries. On some occasions, one of them is easier. On some occasions, the other one is easier. It will be your, you just don't pick one of them. Try to know more than one method. This will benefit your analysis much more in a better way. Now let's try to go and find the corresponding Thevenin or Norton equivalent circuitries for this example. As you can see, using source transformation here will not be a good one. But since we have only one dependent voltage source in here, maybe finding the equivalent Thevenin resistance is kind of easy. Just short circuit these two terminals and looking from this side on, see how the resistors are connected. When you just short circuit that portion, you see that this 12 ohm will be directly connected to the terminal B this time. So I can just take that and just put it in here and calculate the resistance value. Just use this. This is saying that these two resistances are in series, in parallel. The combination of them will be in series with the 8, and the whole combination will be in parallel with 12 ohm resistance. If you do the calculations, you'll end up with 6 ohms. That is the equivalent Thevenin resistance for the circuitry. Now, for the Thevenin voltage, you can use a node analysis or a mesh analysis, whichever you want. In here, your book used kind of it really is a nodal analysis.
Hocam bir şey sorabilir miyim?
Evet, buyur.
Hocam,
bir an duralım.
Bir önceki slayttaki devre dönüşümünü normal delta Y, Y delta şekilde devrelerde de yapabilir miyiz?
Ne alaka şimdi? Anlamadım. Devre dönüşüm. Şunu mu?
Evet. Şu aşağıdaki sol aşağıdakini sağ
Yalnız bak,
aşağıdakini
sen
direkt
burayı mı Y olarak gördün?
nereye hocam? Nereye gösteriyorsunuz?
Şimdi ulan kırmızıyla çizeyim, belki daha güzel gözükür. Şu bölüme mi Y dedin?
Evet.
Ama o Y'nin iki terminaline 12 volt bağlı. 12 ohm bağlı. Yani burada aslında delta Y ile alakalı bir şey yok. Bu çok rahat hesaplanabilecek bir devre. Burada delta Y yok yani. Delta Y de böyle nedendir bilmiyorum. Belki öğrenciler bir kere ulaştıktan sonra bir obsesyon mu ne oluyor? Her gördükleri şey delta Y diye saldırmaya çalışıyorlar. O bir transformasyon yani. Bir örnek olarak yaptık. Güç devreleri dışında
Hocam ama
çok büyük yer... Buyurun.
orada 5 ohm nasıl 20 ohm'a paralel geldi bir anda?
Hadi bakalım.
Orayı birleştirdik de 12
Bura
ohm'a karşı
birleşince
durumu
bak,
biraz...
bununla buna da aynı. Onu kulağını çekip buraya getirelim. Buradan bakalım. Bak. Buradan bir tane geliyor oraya. Buradan bir tane geliyor oraya. Sanki bunlar paralel.
Yok, paralelliğinde sıkıntı yok da 12 ohm'a karşı durumu. Yani şöyle, mesela ben 5 ohm'la 12 ohm'un kesiştiği noktaya bir harf versem. Diğer
Bak, o
tarafa da bir harf versem.
Görüyor musun? O B ile aynı.
Evet. Üst tarafına peki?
Üst taraf dediğin şu 12 ohm mu?
5 ohm'un 12 ohm'a 20 ohm'a giden kısmı. 5 ohm'un. Yani 5, 8 ve 20'nin kesişim noktasına bir harf versem.
Tamam.
Oradaki o harfin karşılığı yok sağdaki.
Bak, C burada şu anda. Değil mi?
Ha.
O nokta aynı gibi sanki.
Tamam, şimdi oldu hocam.
Tamam.
Anladım.
Nerede kalmıştım? Let me take my English hat back. Okay. Now I'm going to calculate the open circuit voltage in order to get the Thevenin voltage. Just assigning current values like this, that's the way your book did it. You don't have to do it this way. I mean, you can do a nodal analysis or a mesh analysis. That will not really be different. Just put one node in here, just calculate the voltages in here. The currents going into that, but it's kind of done a little bit differently in here. By using that calculation, you can easily calculate the I of S value, which is the summation of those two currents, I1 and I2. Since this is open circuitry, the current coming to this side will be 0. That's what the solution is trying to say. And just using that, you can find the value of that value in here. And without loss of you can, using those little calculations, you can easily find the voltage difference between those two terminals, which comes up to be 64.8. Just nodal analysis, nothing fancy. So the corresponding Thevenin equivalent circuitry for this circuitry in here can be calculated in this way. You could have used in the other ways, the other methods, all will end up with the same result. Now, what happens when we have an independent current or voltage source in the circuitry? Just something like this. There are the same methods, all the methods we used before are still applicable, no problem with that. But you can do something extra. Instead of just short circuiting or open circuiting the circuitry, those are still valid, by the way, you can apply a test voltage, a dummy variable, as if you're applying a current value or a voltage value between those two terminals. By that way, you'll be able to find the corresponding I of X directly, and just don't worry about this dummy variable. Just like say V in or VI, VP, whatever you want to say, or I or current value. Don't worry, it will at the end be cancelled out. Let's just try to do it through an example in here. We assume that we apply a current in a small test current source in there. It doesn't have to be small, by the way. Just the value of I of t it will not be just used anywhere. Just use in here. They use the current source. It could have been a voltage source too. We'll say that okay, the I of t is just forced to enter the circuit this way. So by just using this node analysis, you know that 2I of x is coming from this side and I of x is coming in here. So 3I of x will be coming in here. ITH is supposed to come from this side. VTH will be just using the node analysis in here. You can say that 3I of x plus I of t will be equal to the current getting out of the circuitry, which is VT divided by 1. So VT is kind of minus 5I of x, or I of x is minus VT divided by 5. Now I'll use this value in the rest of my analysis. See, just to calculate the value, as VT, it will be in terms of V of t. And since at the end, to calculate the resistance, I'll be dividing V of t by I of t, I'll get a value that the I of t value I used over there will be cancelled out. And I'll end up with 5 divided by 8 as the V Thevenin. Just finding the RTH value by just disabling the voltage source and open source, represent, instead of instead of the current source, put an open circuit on there. Will just work, but don't do anything with the dependent source now. For that, just apply a current, a dummy current or voltage source, whichever is suitable for you, to calculate the value of RTH. The rest is just exactly same as we did before. Just do an open circuit voltage reading from this portion. Then do a normal node analysis for node 2 or whichever node you want. You'll end up with finding the equation for VAB, and that will give you the Thevenin voltage for that voltage representation for that circuitry. Now, one more thing that we're going to be seeing on this day is the maximum power transfer. What Thevenin and Norton equivalent circuitries gives us is for a load resistance, we want to know what will be the maximum value of power that can be delivered to the resistance. That value is proportional to the resistance value in here. And instead of doing the analysis for a whole big circuitry, we can just take this Thevenin equivalent and put a load resistance in here, and let's try to find what will be the maximum, what will be the value of R of L to get maximum power transfer. For this circuitry, the power dissipated on R of L can be found just using V of L multiplied with the current passing through that, or just I squared times R of L, or VL squared divided by R of L. VL squared can easily be calculated using voltage division. Do you remember the voltage division? Multiply with R of L, divide by the sum of the resistances RTH plus R of L. Multiply this with the voltage supplied to the resistance in here, supplied to the circuitry in here, RTH. This will give you the voltage used on this resistance, dissipated on this resistance. I mean, that the voltage, this resistance on this resistance value. So get that value, take the square of it and divide by RL. You'll end up something like this. Now, how can I find the maximum value of that? I need to find the extremum values with respect to R of L of this equation in here. So I take the partial derivative with respect to R of L and just equate that to 0 to find the maximum value, or really the extremum values. And I end up finding that R of L is equal to R of TH. So that means we have maximum power transfer to the circuitry when the Thevenin equivalent of that circuitry is equal to the load resistance. Kind of nice, isn't it? Ulan dinleyen var mı beni? Kendi kendime mi konuşuyorum? Yes, I'm
Dinliyoruz
speaking.
hocam.
Okay.
Yes.
Now, is everything okay with this calculation? I hope you know how to take the partial
Yes.
derivative. Aranızda hala matematik 2'yi almadan devam eden varsa geri dönüp matematik 2'yi alsın. İleride sorun çıkaran bazı hocalarımız oluyor. Benim gibi. Bitirmeyi falan vermiyorlar öğrenci. Öğrenci ağlıyor. Yine de bir şey değişmiyor. Yine de vermiyorlar. Okay, so the maximum power transfer, for the maximum power transfer to happen, the load resistance must be equal to the Thevenin equivalent of that circuit, Thevenin equivalent resistance of that circuitry. And the corresponding power transfer, the maximum power transfer, the corresponding power transfer for when the loads are equal to each other is 4TH squared VTH squared divided by 4RL. This is the maximum power that can be transferred to that load circuitry, load resistance really. So let's do an example in here. Let's make the circuitry a little bit complicated by just like this. Now we want to learn what will be maximum power that can be transferred to the rest of R of L value. Now to find that, the best way to find that is just find the take that portion out of the circuitry and find a Thevenin equivalent between those two terminals, A and B. And when you find the Thevenin equivalent resistance for that circuitry, RL should be equal to that value to obtain transfer. Let's try to do it the standard way. Let's find the open circuit voltage between those two terminals. That V of AB at that portion will be equal to the V Thevenin. So just after removing the circuitry, let's do a kind of mesh analysis in here. Assign 3 currents passing through each mesh. One is this one, the second is this one, the second is this one, and the third is this one. Let's, for the first mesh, write the mesh equation. We'll start from one node and write the voltages that are inside that mesh. If you start from this side on, that is, for this one, it is 480 volts plus 6 ohm multiplied by I1 minus I2 plus 40 ohms multiplied with I1 minus I3 and 4 ohms multiplied with I1 only. This is the first mesh equation. I mean, you can simplify it to have a value in this, to have the equation in this form, but I'll go to the second mesh. In the second mesh, we don't have any voltage supplies. So I'll start from here and write the mesh equation. That is 4 times I of 2 plus 8 times I of 2 multiplied by I of 3 and 6 times I of 2 minus I1 will be equal to 0. Or you can easily just say 18 I of 2 minus 6 I1 minus 8 I3 is equal to 0. This is the second mesh equation. For the third one, we got to be a little bit careful on that because I got to write I of B because there's a dependent source in here. That is 20 I of B. I of B, as you can see, is I1 minus I2. Just write that equation in terms of that. That is 40 times I3 minus I1 plus 8 times I3 minus I2 plus 20 times I of B. I of B was I1 minus I2. And 2 times I of 3 should be equal to 0. We have 3 equations. This is the third mesh equation, by the way. 3 equations and 3 unknowns. Unknowns are the current values. And you can easily find the current values. When the current values are found, I1, I2, I3, the open circuit voltage tree will be the voltage applied on this 40 ohm resistance. That is 40 times I2 minus I1. That will give you, sorry, I3 minus I1. That will give you the value. So it's 48 ohms. I mean, to find the equivalent Thevenin resistance, you can just short circuit those two terminals. When you short circuit that terminal, beware that we don't need that 40 ohm volt resistance anymore. It's just shortcut to this. Since these two terminals are shorted, we can easily neglect that. And just we have this time, I mean, let me make it like this. Oh, can I just make that pen a little bit bigger? Anyway, let me use that. Just ignore this value now. Now to calculate I circuitry, just write 3 mesh equations, I1, I2, and I3. Just do the same kind of analysis. This time I3 is equal to I1 minus I3. I short circuit will be equal to I1 minus I3. You'll end up with 3 equations and 3 unknowns. When you solve those equations, you'll be able to calculate IC of I short circuit between those two terminals. And that is also calculated, dividing the voltage V Thevenin by I short circuit, you'll be able to find equivalent Thevenin resistance in here. And you'll end up writing this thing. Now, go back to the circuitry in here. The equivalent circuitry, when you look at between those two terminals, is simply a voltage source in parallel, in series with the resistance. And the maximum power transfer to the load can be done when the load resistance is equal to the Thevenin, that is 12 ohms in here. And the value of the maximum power transfer is VTH squared divided by, what was that? Well, let's go all the way back. VTH squared divided by 4RL. That is the maximum power transferable to the load. Before going to the next example, how is it coming? Can everybody follow me? Ulan Adile Naşit gibi miyim? Hepinizi mi uyuttum? Seems yes. Okay. Let me go to the next example. Let's find the Thevenin and Norton equivalent circuitries and find the maximum power transferred between these terminals A and B. You got to be careful about this one. Really, there's nothing to be careful about. Just find the open circuit voltage and short circuit current, and that'll be it. This is so easy. Why did I choose this example? Because it really is very easy. When you open circuit these two terminals, the voltage is same. There won't be any current coming to here. So the voltage is just equivalent to the value in here. And that is directly equivalent to, just write the node equation on here. Assume that a current is going to that, and this current is coming here. The current on this side is V of X minus 4 divided by 2, which will equal to the Vx divided by 400. You can easily find V of X just like this, and V of X will be 8 volts. That is V open circuit, which is also equal to the V Thevenin. To find the current, just short circuit those two terminals. That's what we did in here. And just do the same analysis this time by assigning a node in here. Let's say it's node 1. The voltage on node 1, something went wrong. Beni duyabiliyor musunuz?
Yes.
Evet.
Evet.
Duyuyoruz hocam.
Bir olaylar oldu. Ben de anlamadım. Neyse something went wrong dedi. Tam da böyle short circuit yapmış. Şu şeyi I short circuit hesaplamaya çalışıyordum. Dikkat etmeniz gerek. Let me put my English hat back. Sorry. Just take this note. The voltage in here, let's call it V1. V1 minus 4 divided by 2. V1 divided by 3 will be the current going to that node, and this will be equal to Vx divided by 400. Vx is the, as you can see in here, Vx is simply 0 for the circuitry, since we have short circuited in here. So just neglect this dependent source for this analysis. That'll be it. The current passing through those two terminals is 4 divided by 5K. I find the short circuit current and open circuit voltage. That's it. Just dividing those two values to each other. I mean, my Thevenin equivalent circuitry is something like this: 8 volts in series with a 10 kilo ohm resistance. The maximum power delivery can happen when this RL is equal to RTH. So for the maximum power transfer, RTL will be 10 kilo ohms. And to find the maximum power transfer, just that's VL squared by, there has to be a 4 in here. I probably missed the 4 in here. So this is 40, this is 0.4 milliwatts. Oh, sorry. There has to be a 4 here, but 4 is also divided in here. The answer is correct. is 8 times edge 64 divided by that will give me 16. There's a 4 missing in here, nothing else. The rest of them is true. It's correct, sorry. And we can just use another method. I mean, using that tierce, since we have, just a second, to calculate the resistance, we don't need to calculate the short circuit current. We can just do that, insert that test source in here, and just short circuit independent source, short circuit independent voltage source, open circuit independent current source. We don't have a current source in the circuitry anyway. Just do a nodal analysis and find the corresponding. I'm saying VT in here, but as I said before, VT and IT will cancel out. Don't worry about them. Do a nodal analysis in here and easily calculate the resistance value. That will be 10 kilo ohms, same as before. Is everything okay? Can everybody follow me?
Yes.
Bir yesinizi yiyeyim sizin. Stop recording. Yep, I'm